Well, we're reaching the end of this section. We just have some more discussion of p-value. It says here that smaller p-values indicate stronger evidence. Smaller p-values, stronger evidence. Larger p-values, weaker evidence. Against the null hypothesis. So you're trying to gather evidence to claim the null hypothesis is false. Small p-values would lead you to believe that. Large p-values would lead you to go, oh well, it's probably random variation. We usually use significance level alpha equals 0.05 and reject if the p-value is less than 0.05. So typically for any alpha that you might choose, we're going to reject if the p-value is less than alpha. So no matter what you'd use for a significance level, which is stated in advance, use significance level 0.05. What are the conclusions of the test? Well, you compute the p-value, you compare it to 0.05. If it's less, you reject, and if it's not, you fail to reject. And you claim that you're doing that at the level that's been given to you to use. So usually 0.05, sometimes 0.01, sometimes even other numbers are used for a significance level. But that's what you compare the p-value against. And that matches up with comparing the z or the t, if alpha is 0.05, to something like 2. So it's just a unified way of doing it without actually mentioning which test statistic you're using or what the procedure is. It's about strength of evidence. And the same level of alpha or the same significance level, if it's broken and the results are that unlikely to occur, if the null hypothesis is true, it's the same strength of evidence across all different hypothesis testing frameworks you might run across. So alpha is 0.05, just more or less says, pretty much you wouldn't see this randomly, so I think something's happened. And alpha of 0.01 says it almost never happens like that randomly, so I'm pretty sure something's happened. And smaller, if you use an alpha even smaller and you reject the null hypothesis, then you're even more sure. Now what you do though, what you could do is, well, instead of declaring a significance level up front, you just go ahead and compute the p-value and see how tiny it is. So that's another approach. A p-value less than the significance level causes us to reject the null hypothesis at that level. Otherwise, we fail to reject the null hypothesis at that level. So I said another approach is just to tell whoever asks you to do the research what the p-value is and let them decide what they want to do with that number. And then they'll see the strength of the evidence and they can decide, is it so strong I want to go forward and make a decision, or is the decision so expensive and I've got a p-value that's around 0.05, so I'm sort of sure it's not random, but I want to be more sure. So let them decide that. Don't you set it up for them. That's a possible way to go forward. So here's 3 experimental situations, or observational study situations, where we have a null and alternative hypothesis. Here's a proportion in the population, it's a half, but you happen to think it's bigger than a half. Here's the mean for the population is 120. You happen to think it's not 120. And here's the null hypothesis, 4.3. You happen to think it's mean. The mean is 4. Here you happen to think it's less than 4.3. Well, and then over here is the quoted significance level you're supposed to be using. 0.05, 0.01, 0.2. Someone told you that's the level you're going to be using. What are the results? And then you do the p-value calculation, which you haven't done any yet, but suppose you did it, and you got 0.03. We're wondering what the conclusion is. We got 0.03 for all of these. But we're using different significance levels for each. And so we have to decide, based on the significance level, what do I do? Well, I just compare the p-value to significance. If it's less, I reject the null hypothesis. So 0.03 is less than 0.05. You reject HO, and you accept HA. So you say P seems to be bigger than 0.5. Okay, in the second one, we're using a significance level of 0.01. Here's my p-value of 0.03. It's not small enough. It's not less than 0.01. So here, we failed to reject the null hypothesis. And we can't accept HA. So as far as we're concerned, the mean isn't different from 120. It's pretty close to 120. It's not far enough away that you wouldn't see those kinds of results with your test statistic if the mean was 120. So, you'd probably be pretty sure the population mean isn't exactly 120. But if 120 was the mean, those kinds of test statistic values could happen about this proportion of the time, and you want that significance level when this isn't smaller than that, so you fail to reject. It would be considered statistically significant, but somebody wants even stronger evidence than that. So not just, I think it's not random variation, but I want to be really sure it's not random variation. So you don't quite have that with 0.03. And then for the third one here, I'm using significance level 0.2, which is not a very strong level of significance at all. It wouldn't take much of an unusual value for you to say that the mean's not 4.3. I get a p-value of 0.03. It's a lot smaller than 0.2. So since 0.03 is a lot smaller than 0.2, p-values less than the significance level cause you to reject the null hypothesis. So we're going to reject HO at the 0.20 level. Sometimes we'll say alpha equals 0.2 level, and accept HA and claim the mean might be less than 4.3. It looks like it might be. Of course, that significance level is not very small, so I don't have a lot of confidence in that truth. But as far as we're concerned, this particular test at that significance level causes us to claim the mean looks like it's less than 4.3. But we'd have to say, on top of that, we're only using significance of 0.2. So it's possible the data that we're looking at that's causing us to say that is really random variation, because that's not a very small significance level, so you don't have to be that far away from where you should be to cause the test to reject the null hypothesis. So let's see. So the next order of business is to actually put all the pieces together and from start to finish decide on the null and alternative hypotheses, figure out what test statistic you're going to use, collect some data, compute a p-value, compare it to your level of significance that you have chosen or was given to you, and then state conclusions. And finally, the conclusion should be stated in the context. Here I didn't even make any description of what the context is. What are we measuring? What do we want? What is this about? What's supposed to have probability 1/2 of happening? Who has mean 120 or mean 4.3? What are those things? And what does it mean for the mean to be less than 4.3 or not equal to 120, and so on? So in the context of things, sometimes you'll see how the hypothesis testing can be used in real life, but we haven't gotten to that place yet. We're just studying the procedure, and now we'll look at some actual examples and see how the conclusion is stated in the context of the problem. That's coming up, but right now I'm closing off this screen.